So I want to look at special kinds of linear programming. Special kinds of linear programming. There are three main special kinds of linear programming formulation. And this is in a basket of information learning known as the network flow models. Network flow model. Most or all of the network flow models can be handled using these special kind of linear programming. In other words, there are ways of solving network, but you can also use linear programming in solving it. One approach is using the Excel. The other approach is using the simplex algorithm. Now, let's take the first of the linear programming model that can be handled using network flow. And this is known as a transportation problem. A transportation problem. In basic terms, a transportation problem happens when a product is transported from the supplier to the demander at a minimum cost or at a minimum distance, at a minimum cost or at a minimum distance. The supplier is known as the source. The demander is known as the destination. Each source is able to supply a fixed number of items, and each destination is able to demand that fixed. In other words, what the demander is demanding, the quantity is not the same as what the supplier is supplying, not necessarily. But the transportation will incur a cost known as CIJ. And therefore, these are the elements of notation you should take note of. I wouldn't want to go through the notations because they are self-explanatory, okay? But let's try and get them. The whole idea is to minimize this whole cost multiplied by the item or the amount or the decision variable. So you have each coefficient multiplied. But why do we have a double summation mark? The reason why we have a double summation mark is because you are moving the items from I to J. In other words, you are moving from one node to another node. Okay. And so you are first of all multiplying something by something, and then adding them, and then multiplying something by something. We'll talk a lot about node and ax very soon. So you have a objective function, which is a minimized objective function. And like I said, it can be cost or distance. Subject to the following constraint. Emily, what does this remind you? Those of you who have been taught by me on, operations, decision, and risk, what does this constraint remind you of?
Anyway. Not the DEA constraint, the weighted sum of input and output.
Not the DEA constraint, but the linear envelopment analytics constraint.
Okay.
You got to start using those terms before you start getting confused later on. And then when it hits you, you say A, but then you have spoiled already your matter. So you have a function, objective function, subject to this constraint. As you can see here, this is the weighted input, less than or equal to the supply. And then this is the weighted output, less than or equal to the supply here as well. Of course, the non-negativity constraint still stands out there. We are going to take some methods of driving this. There are two methods for solving a transportation problem. Okay. There are also two methods for identifying the initial feasible solution. The initial feasible solution must be identified first. There are three of them: northwest corner method, minimum sales cost method, and the Vogel approximation. We shall look at these two of them. Then, to get to the optimal solution, remember, these are the initial feasible solution. You get the optimal solution, you need to have the stepping stone method and the modified distribution method. We're going to look at them. Okay, first, let's try to understand an example of a transportation model. Wheat is harvested in the Midwest, stored in grain elevators in 3 cities. The cities are Kansas City, Omaha, and DM. So remember, the wheat or the corn is harvested in the Midwest and stored in the grain elevators. The grain elevators are in 3 cities. The elevators are the ones holding these wheat. They will now supply these wheat to 3 different flour mills. The flour mills are located in Chicago, St. Louis, and Cincinnati. They normally use something we call railroad cars. It's like railway, but then each kind of block is not for human beings, but it's for those particular wheat. Each of them can carry 1 ton of wheat. The elevators supplies the following tons of wheat to the mill every month and at a specific cost. So Kansas City supplies 150, but this 150 will go to Chicago, St. Louis, or Cincinnati. We don't know which one yet. Omaha supplies 175 tons. It will go to Chicago, St. Louis, and Cincinnati. But Chicago is only receiving 200. So even if Kansas City sends all the 150 to Chicago, Chicago is not getting what is demanded. And so it will need more. What you got to know here is that these 3 cities are owned by the same company, okay? And then they are supplying it to, 3 different places. It doesn't necessarily have to be 3 by 3. It can be 3 by 4, 3 by 5, or anything. In this very context, the total amount of supply equals the total amount of demand. We'll come back to that point. The cost associated with sending from Kansas City to Chicago is $6. From Kansas City to St. Louis is $8. From Kansas City to Cincinnati is $10. The cost of sending from Omaha to Chicago is $7. Omaha to St. Louis is $11. Omaha to Cincinnati is $11. And then on and on and on. Here is a question. Define the decision variables for this transportation problem. Now, even if you are not told to do it for this transportation problem, something in the question will tell you that it's a transportation problem because you were told that you are transporting the thing from this to that. 2, after defining the decision variable, develop a network model. Show all the costs and the decision variables. Formulate the model. Solve in Excel. You guys are not going to solve in Excel, but you're going to solve. In fact, you might solve it in Excel, but the key point is to use the simplest algorithm to do the solution. Okay. Let's try to understand the decision variable. But before you understand that, I want you to look here. This is a source, and that is a destination. This is called I, and that is called J. Anytime I can transport from this node to that node with the arrow showing where I'm going to. The nodes, write it down, the nodes are the constraints. The acts are the decision variables. The nodes are the constraint, the acts are the decision variables. Okay. Now, if we have 6 nodes, how many constraints do we have?
6. That's 6 constraints.
Okay. Now, if you have 2 nodes and another 2 nodes, how many decision variables do you have?
You have 4.
How many constraints do you have?
4 constraints.
If you have 3 nodes, 6 nodes in all, how many decision variables do you have?
That's 6.
No.
Doc 9.
9. You have none. So be very, very clear with the decision variables. The decision variables are the acts. Because when you start from here, it will go there, it will go there, it will go there.
Okay.
And the other ones will also repeat that process. How you define the decision variables is simply saying that Xij refers to the number, in this case, the number of tons of wheat. I'm writing it for a reason. Number of tons of wheat. From, if you don't want complexity, you can just say from node I to node J. Simple. From node I to node J. And then you indicate that where I is 1 to 3 and J is 4 to 6. We'll come and explain why we label them like that. And I is not equal to J. Now you remember that the source in this very example, the source are Kansas City, Omaha, and DM. The destinations are Chicago, St. Louis, Cincinnati. So when we have to actually draw the network graph model, if we have to draw it, we need to indicate which ones are the source, the demand, the supply, and which ones are the supply or the destination. Now, we will use numbers all the time to label them. Now, in this very example, you all agree that the source were how many? 3. Do you agree? The source were 3.
Yes.
And then the demand was what?
Also 3.
3.
Also 3. So if you are drawing your network, it will just be the one I have here, isn't it?
Yes.
Good. And now how you label it is more important than anything. So I'm going to just do one. I mean, normally if I'm by you, I would have gone around to see. So this is how you label it. The first one is circle, another circle, and another circle. But you label it as 1, 2, and 3. These are the supply. Then it will continue. The numbering will continue. In this case, there were 3 demanders. So you continue as 4, 5, and 6. On the right side of each, you will write the tons that were supplied or demanded. Okay. So when you take this one here, the tons that were supplied from Kansas City was 150. So you write 150 here. You write 175 there. And then you write 275 here. For the demand, you will write 200 for the first one, 100 for the second one, you attach it to it, and then 300 for the last one. Then at the bottom, you put the total supply and the total demand in your graph. You should be doing it whilst I'm doing it. Okay. The next thing you will do is to draw each arc and label the arc at the same time. Draw each arc and label the arc at the same time. And by arc, I mean the lines. So you start with the first one. The arc from 1, so that is from Kansas City to Chicago, you move from this side to this side, and then you use an arrow. This arc must be labeled, and the label should simply be the numbers from the from to the to. So the first one will be X14, which will indicate the first decision variable. Then you draw the next one. You have to label it X15. Then the next one, X16. You have to label it before you go to the Next one. Now, after each first label, you should write the cost, but the cost should not be attached to this. It should be towards the end. So the first one, the cost is $6. Second one, the cost is $8. Third one, the cost is $10. Now, if you don't label them quickly as you go, you will see that you get lost. Because sometimes the thing becomes mania, then you don't even know which line even is going where. Please know that sometimes in an exam condition, you can have like, I've seen a question where you have 12 here, 12 there. So we are talking about how many decision variables here? 12 times 12.
144.
So you can see. So you have to draw and draw and draw and draw. Okay. All right. So can you do the next one? Can you draw the next one?
Yes, Doc.
Good. So the next one will go from where to where?
Doc, from 2 to 4, 2 to 5, and 2 to 6.
So you see, as you keep adding, they become manya, manya, manya. And then for
So
each
the first one will
how
be
will you label them?
X24. Doc, X24 for the first from 2 to 4. And the amount is 7. X25, amount is 11. And then X26, the amount is 11.
So when you do that, then you do the next one, you do the next one, and they all look great. Remember, the cost must be added whilst you are writing each decision variable. That's the first part. Any question? So you should be able to do this by yourself when you tackle it. So that's the first part. Define the decision variable. We've done that. Develop a network graph for this problem showing all the cost and decision variables. We just did that. The next is to formulate the mathematical model for this problem. Now, let me show you something. This was one we drew. Here, I used ABC, but please don't use ABC. I later realized that it's best to use 4, 5, 6 so that it becomes easier. And then you get something like this. So you are now going to formulate the objective function. And anytime you are formulating the objective function, don't look at the question. Look at what you have drawn. Because what you have drawn has got all the labels. Okay, what you've drawn, it has all the labels. So use that. So the first thing you got to ask yourself, is this a minimization or maximization problem? Who can tell us?
The minimization problem.
Good.
No.
So you start with your Z max.
Doc, Z-min.
Z-min.
Very good. Now I know you are there. So you do your Z-min, and then you write equal to, let's start writing the objective function. Who can tell us the first one?
Doc, 6x14.
So 6x14.
Plus is it? Is it 8? Is it 8? Yeah, okay. 8x15 plus 10x16. Jerry, are you continuing or should I continue?
Jerry, continue.
Plus 7x24 plus 11x25 plus 11x26.
Okay. Eugene, continue.
Doc, there is not 11x25.
It's 11. It's
The
11.
last one should be, it should be 5.
What should be 5?
So it should be 5x26, not 11x26.
No, it's this one that we are doing, Chief of Staff. I don't know where your eyes are.
Can we go back to
We are where we are.
No, he has finished the first one. Or he has Simon. They've done the 6,
I
8,
understand,
and
but
10.
when I wrote I saw 5 there, not 11. So if we can go back on the table.
No, this is the right one.
Okay.
So look at it. This is already printed one. So
Okay.
this is the right one.
Okay, so let me continue. So the next one is plus 4x3
1.
Nobody should help him. Let him do it. Because those of you who are helping him are getting it wrong yourself.
4x3
X
1 plus 5x3
That's
2.
wrong.
Okay, 4x3 this is 6, right? So 7.
That's wrong.
4. 4x3
Hey,
4.
I say nobody should talk.
Sorry.
Okay, 1, 2, 3, 4.
Now, when Emily was saying it, it looks easy to you all. There's also a reason why I want you to say it, because if you don't say it, you will not even think that, oh, why am I getting it wrong? Solomon, are you here?
I'm here.
Okay, take over.
Okay, so 4x34 plus 5x35 plus 12x36.
Very good. So this is how you got to formulate it. This all together will give you the combined objective function. Then you bring your subject to, and then you write a constraint. Now pay attention here. When it comes to the constraint, it's easy, but not easy. The constraint, you have to look at the graph. That is why I keep saying that if the graph is wrong, you're going to be struggling. You have to look out for all the arcs that are leaving the first constraint. The constraint, remember we said the constraints are for the nodes, and there are 6 nodes. So you're going to calculate 6 different constraints. The first constraint will be number 1 here, and you're going to look at all the arcs, not with their cost, just the arcs, the name of the decision variables that are leaving the circle. And then when you're looking at this second one, you're rather going to look out for those arcs that are coming to the circle. So let's take the first ones that are leaving the circle, and you're going to add them. So number 1.
Okay. Now, can I take it?
Yeah.
Okay, so number 1, for Kansas City, we are going to have x14 plus x15 plus x16 less than or equal to 150.
Okay, we'll come back to that.
Okay.
So at this stage, before you come to the 150, you have to decide whether you are dealing with a balanced transportation model or an unbalanced transportation model. Now, pay attention, it's in the notes though. A balanced transportation model is where the total supply equals the total demand. An unbalanced transportation model is the one where the total supply is not the same as the total demand. Either it is above or below it. So looking at our example here, are we dealing with a balanced or unbalanced? Simon.
balanced.
Good. Now pay attention here again. Whenever you are dealing with a balanced transportation model, the constraint will all have equality sign. All the constraints will have equality sign when you have a balanced transportation model. So the sign that should come here will be equal to 150. Guys, do you follow? Do you all follow?
Yes, Doc. We are following. Yes, Doc.
All right. Now, Albert, walk me through the next one, the next constraint on the right, the top one here.
Okay, so that would be x14 plus x24 plus x34.
Very good.
Then it would be x15 plus x25 plus
No.
x.
You are not done with this one.
Sorry,
You're not done with
so
this
it's
one.
done. It's equal to. Oh, sorry. Is equal to 175.
That's wrong.
Hey, wait. The receiving node, which is St. Louis, is 100. Sorry,
Wrong.
St. Louis. The demand for St. Louis is 100.
It's 200. Oh,
We are doing for Chicago. Sorry, 200. I didn't.
200.
That's what it
Yes,
is. I keep saying pay attention, everybody. Pay
yeah,
attention. Pay attention.
200. Yeah.
So this is how you write it. And then you can formulate each of these constraints. Okay. Because you have already identified that it's a balanced transportation model, you know you're going to have equality all through. Okay. So this is the balanced transportation model. The total supply equals the total demand. Now, if, and this is a final formulation, the only thing left now is to add your non-negativity constraint, you are done. I made a typo by writing maximize, but this is supposed to be minimized. So please take note. Who is not clear? Don't forget the non-negativity constraint. Now, what if we were dealing with an unbalanced transportation model? What if demand at Cincinnati is not what you see, is not 300, this last one. Demand at Cincinnati, what if it's not 300? What if that demand is not 300, but it's 350?
That will be an unbalanced.
Which one is more? Is it
So
total
if it is
supply
350,
or
it will be
total
more.
demand?
total demand will be more.
Demand will be more.
Demand will be more. Now pay attention here. So whenever demand is more, like in this case, what you do is that the one that has the demand being more should have less than or equal to. Write it down. The one that has a more demand should have less than or equal to. The other one must remain as it is.
The statement all over again.
I said that whenever demand is more than supply, demand will have less than or equal to constraint, but supply will continue to have equality constraint. And when supply is more, the opposite will happen.
So you say whenever demand is greater than supply, supply will always have an equality constraint. And what will happen to demand, please?
No. I said whenever demand is more than supply, that demand, which is rather more, is always the fact that the one that is more will always have the less than or equal to constraint. The one that is more. Is the one that is more. That will have the less than or equal to constraint. The other one will have the equality. Okay.
Okay.
So, in a transportation model, we have to solve for the initial feasible solution. And there are three methods: northwest, minimum cell cost, and Vogel approximation. Now, what are we looking for? What are we looking for? What are we looking for? What are we looking? We are looking for the decision variables. Okay. Once you get the decision variables, which are the Xij, then what do? You find the total cost or total distance. So first, you need your Xij because you have your Cij. You need the Xij values. Once you get the Xij, you'll get a total cost or total distance. But the solution, some of them are not best of solutions. Some are best. The best of solution is the cost that is a little bit higher than the optimal solution. So we're going to take one approach to dealing with this way of solving the thing. Now, like I said, you can also solve it in Excel, but we are using this. So the first two methods for solving the model, the optimal solution, not the initial feasible solution, but the optimal solution. Emily, you might see some common names here. The first solution, okay, the optimal one was known as the stepping stone method. And the other was known as the modified distribution method. Both of them in 1953 were developed by Chance and Cooper. So Chance and Cooper developed the stepping stone and then the modified distribution method. The modified distribution method gave a quicker, that's why it's called modified, a quicker computational approach, and that was in 1955. In 1947, already before, Koopmans had produced the optimum utilization of the transportation system. They had set the stage towards this stepping stone method. So we are going to take the first one. Before we come to the stepping stone method, we have to find the initial feasible solution. And you use the northwest corner rule. Northwest corner rule. Guys, pay attention. The first thing you got to do in this method is that start from the northwest corner of the tableu. So if I do this thing like this, and I say A, B, C, D, E, F, G, H, I. Where is the northwest corner? You can tell
A.
us. Where is the southeast
That is the
corner?
J.
Hey, who said J?
Said J, Jerry.
Northwest corner is A, it's not J. Northwest corner is the top leftmost part. The top leftmost part of the table. Okay. So what you do is that you start from there and you exhaust the supply. And then you finish the supply before you go to the next row. You're going to share that supply for the first row. Exhaust the demand before you move to the next one. So let's try it and see. So first, we need to know the entire total supply table. So look at it, this entire table. In there, you have the cost, 6, 8, 10, 7, 11, 11, 4, 5, 12. And then the total supply for Kansas City is 150. The total supply for Maha is 175. Total supply for DM is 275. We are going to start from the northwest. So at which number are we starting from?
6.
6. But we are not going to take the 6. We are rather going to see that 6. Okay. The supply there means that you are supplying from Kansas City to Chicago. And how much is Kansas City supply? 150, right? So you give the whole of this area here 150. You pour all the 150 to that. Okay. Because that's all that Kansas City has. But then when you look at it, Chicago was not expecting 150.
Oh, yeah.
Chicago was expecting what? So
200.
You take the 150 here. So that means that even though the 150 has been sent, who's talking plenty like that? Okay. Solomon, he's not paying attention at all. These are the people I know who are not serious. So when you take Kansas City, you will see that You see that DM demand for Chicago is 200. So there's how many more left to balance that section?
50.
50. So you will now, because we have exhausted the 150, you will come and take the 175. How many will you take from that?
50
No, 50.
And you supply it to which number there?
to A.
Which number would that
Chicago.
25 go to?
No, to B.
No.
Mm.
You have to
To A.
exhaust. Remember the word we said, exhaust, before you go to the next.
Okay. No, still to A.
No, because A has finished. We move, watch it. We move from 150 here, then we sent everything to A, A6.
Okay.
So everything here is left, is finished. We have nothing else to do there in that row. But then
Okay.
in this column, we've not exhausted it because to balance it, we need something in this column. So you go to the next
Okay.
row, you take,
So it's the 7.
we know that we need 25 to top up. So you take the 25 from the 75 here.
We need 50.
No, 50.
You take the 50 from the 175 and it is left at 125. You add that
Yes.
50 here. And now you've been able to balance that section. You are left at 125. You keep going because here you ask yourself, you keep going because we've not exhausted. We left it 125. We'll supply still on this row. How many should we supply?
Okay. No, 100.
100. And the reason is because that is what is being expected here. So you supply 100 there. How much is left here?
25.
How much do we supply? That whole
25.
Exactly.
25.
You also make sure your eye is watching the rows, the point at the bottom here, to be sure that they are being balanced. Now, we are done with that. As long as this one now is left with 0, we are done with that. We go to the next one. We have a total supply of 275. Where do we supply it to? Can we supply it to 4?
No, 4 is already full.
No.
Can we supply it to 5?
No.
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 So we give all the 275 to 12. 275. Job done. Finished. You have done the northwest corner rule quickly. So now that you are done, you know that according to the northwest corner rule, Kansas City will have to supply 150 to Chicago. We know that Omaha will supply 50 to Chicago, supply 100 to St. Louis, and the rest of the 25 tons will go to Cincinnati. That's what Omaha is going to do. And then DM will supply everything it has to Cincinnati. Cincinnati is already getting 25 from Omaha, so Cincinnati too is sorted. So when you're finding the total cost is going to be found from all those that received allocation, multiplying each one by its corresponding cost. So you can tell me what the total cost will be like. Albert.
So that is going to be okay.
So the total cost would be the 150 by the 6.
150 by 6.
Yes. 50 by 7.
50 by 7.
100 by 11.
Oh, good. And now you move on and move on and move on. And then you can come out with that beautiful result. Okay. So whatever you are seeing here, that is what is happening right here. And when you do that, you realize that the total cost is 5,925 according to the northwest corner rule. You will do this in an exam. So you got to understand. This is called the initial feasible solution. That's what the northwest corner rule is doing. It doesn't give you the optimal solution. It gives you initial feasible. So that means that there must be something that should be done. See, let me tell you the problem with this northwest corner rule. Number one, the northwest corner rule did the allocation without considering the cost. See, if you check it very carefully, everything that was done, when you were allocating the 150, did you take into consideration the $6 cost? No.
No.
So it doesn't take into consideration the cost, and that is a problem. So we need another method that will take care of the cost. And this is known as the minimum cell cost approach. But before we do that, we can actually go, of course, it will take care of the cost, all right, but that one too is not the optimal solution. It is also more or less another feasible solution, if you could remember. So we will use the stepping stone method. That stepping stone, that one, it will give you the optimal solution. It will give you the optimal solution. It will check if a cell with no allocation can be reduced further. We'll come back to that. We'll come back to using this. But let's look at another approach of dealing with this cost method. And that approach is the minimum cell cost. Now, the minimum cell cost doesn't use the quantities, it uses the cost. Whereas the northwest corner
Doc,
rule,
is this minimum cell cost? Cell or self?
cell, S-C-E-L-L.
Okay.
So that one uses only the numbers. It doesn't even take care of the quantities. The northwest corner rule takes care of the quantities, but also doesn't use the cost element, the coefficient. Let's see what the minimum cell cost does. You see, as the name sounds, it will start with the one with the lowest cost. Now, if you check the table carefully, which one has the lowest cost?
Doc 6.
No. Let me just clarify things. The one with the lowest cost, because there's a rule here. The one, because if you don't take the one with the lowest cost, that was not assigned.
It was 4.
Because if
Four.
you go with the lowest cost, you're going to select 4.
Okay.
But the one with the lowest cost, that was not assigned. No, sorry. The one with the lowest cost, sorry. Forget about assignment. The one with the lowest cost, because it doesn't take into consideration the previous one.
Okay, then 4.
Yeah. The one with the lowest cost. So the one with the lowest cost is 4. Okay, so now that you identify the 4, you will allocate there. So you're going to take this 275 because remember they supply. So you take this 275 and pour it here. But how much can you pour?
200.
Good.
200.
So you can only pour 200. Besides, you've also satisfied demand. How much is left?
75.
75.
You assign it now to the next lowest cost. That will go to where?
5.
5.
So you will now have 75 here. Then you are exhausted. You go to the next one, 175 or 150 or whichever one. We are going to now assign it to the lowest cost. What's the next lowest cost?
11.
6.
6. But then 6 has already been what?
It's already been filled out.
It's already filled out. So
Yeah.
what will be the next lowest cost?
8 for
8.
the B.
Good. How
Dog,
much should we
it's
assign
still
there?
5. Dog, it's still 5 because
But 5 has
if
been
you pour
assigned.
out, but that's not the maximum. You can add 25
Yeah, but if
there.
it is not the maximum, you are just going to
It's-
add to the 8 so that it will give the maximum. But you don't give it to 5.
Okay.
5, the supply is full. Has been exhausted.
No, he's not even talking about the supply. He's talking about the demand for it.
Okay.
See, he's saying that 75 It's not up to the 100. So he says it is still 5, but no, it's not 5. It is 100 that we have to top up.
But I thought
Yes, then
the 5, when they get their supply from the 275. So since the 275 is finished, then there's no way they can get that 5 again.
It's balanced on the row.
Yeah, but that is what I'm telling him, that we don't need any assignment for that number 5.
Okay.
The next assignment is number 8.
Yes.
And Simon, whenever you are thinking, think not only in terms of the horizontal line, think in the row as well, the vertical row, the column.
Okay, Doc.
Yeah, don't only look at one side. All right, so how many tons you go to the 8? Taking into
25.
consideration the 20.
25.
So you got 25. Now, how much is left at the supply? 125.
125.
Okay. The next lowest one is what?
10.
The next lowest cost is 10. Now, if you look at its demand is 300. So all the 125 can go here. You have exhausted the 150. You are now left with 11 and 11. The total supply there is 175. Where should that 175 go?
The 11 and C.
11 on C. So you now give 175 to everything here. You add that 175 to the 125, you still balance the 300. Now you calculate the cost, the new cost. So the new total cost, of course, we now know the allocation. So the decision variables, we know how much it's going to be. And the total cost will be what?
So it will be 4 times 200 plus 8 times 25 plus 5 times 75 plus 125 times 10
Now you are changing the algorithm.
plus
You should say 10 times 125.
okay. 11 times 175.
Okay. So if you do this well, you're going to get an answer. And the idea is that because it's focusing on the minimum cell cost, you're going to get an answer which is a bit smaller. Everything we did is here. So this is it. Okay, 4 times 200, 5 times 75, 8 times 25, 10 times 125, 11 times 175. You get 4,550. Is this more than or less than the previous one?
It's less than.
Good or bad news?
Good news.
Good news. So the minimum cell cost approach is better. It gives a lower cost than the northwest corner rule. But check this. So it's less, like we said. Okay, but it doesn't consider. We said that the northwest corner rule doesn't consider cost at all, whereas the minimum cell cost does that. Now, if you use the Vogel approximation, we're not going to work it here. But if you use the Vogel approximation, you're going to see that that one is going to be in between the minimum cell cost and then the northwest corner rule. So the value is going to be between the minimum cell cost and the northwest corner rule. All of them are initial feasible solution. But we need optimal solution. Optimal solution. And to do that, you need to use the stepping stone solution method. So we're going to use the stepping stone solution method, unless you have a question. Okay. So I didn't really go deeper into the Vogel approximation. So that one introduces a penalty cost, but you can look at it later. Okay. Now this is where it gets, loaded. So just pay attention here. After you get the initial feasible solution using any of the three methods, the next thing is to solve for the optimal solution, the true minimum. And you do that using the stepping stone or the modified distribution method. We're going to do the stepping stone solution method manually. How do you start? Well, first thing is that because the initial feasible solution, the lowest point was obtained using the minimum cell cost. Do you remember? We are going to take that one and continue because the minimum cell cost gave us the lowest cost, which means that the person is a bit smarter compared to the others. That approach is better. Okay. So let's start from that corner. Let's remind ourselves a little bit. This was the minimum cell cost, just so you remember. Guys, pay attention here. I've said twice that you should pay attention. We had an allocation for 200, 75, and then 25, 125, 175. Each one also had its own each one has got its own cost and then its own quantity. So the first thing you're going to do is that you're going to start with the one with the lowest cost. Which one is that? Okay. So we are going to first identify all the, see, let me tell you the most important thing about this approach, the stepping stone. Okay. It finds the root that was not used. Okay. One of the empty roots, if you look at it here, some of the roots were used. That's why you have bracketed number. But it's looking for the roots that was not used. But if it was used, it will lead to a lower cost. If it was used. Tell me which roots have not been used or which cells have not been used. In this example,
6.
6 is 1.
Yeah, there's 6, 7, 11,
and 12.
and 12.
Good. So this is what happens. It is going to take each one of them, starting from again the lowest. And then it will ask itself that if it was used, what would have happened? If it was, because you can see that some costs like 8 were used, some costs like 11 here were used, 10 here were used. But then because of the nature of the method, 6 and 7 are not used. So what does it do? First thing is that it will give the lowest total cost for them. So here, it will say that let's add +1 to this 6. Okay. We call it, just a second, I don't know. So we want to avoid constraint violation and infeasibility. So we want to balance the supply constraint by subtracting 1 ton along each row. So when you take here, we are going to subtract 1 ton along each row, okay, and then minus in another row to balance. Because whatever you do must be balanced. So we are going to add 1 here and then know where to balance it. So the moment you add 1 here, now why are we adding 1 here? The 1 here is indicating that this one should have been used. That's why we're adding 1. Okay. We are adding 1 ton to this. And the moment you add 1 ton to this A1, what happens is that you increase the supply for the A. Now, why can we say that? Of course, you increase the supply here. But what have you done to this section here? What have you done to that section here? You've also increased. That's what somebody will say. Are you guys with me?
Not yet, Doc.
Okay. You will not increase it because watch it. We indicated that the key point in the transportation is to find the transportation route that is not currently being used, an empty cell, which will lead to a lower cost if it was used. Okay, that's what a stepping stone is actually checking. Okay, so first you need to check which cells are empty, which cells are not used, and we know all the cells. Okay, and then identify which will give the lowest total cost. And then we saw that it was a 6. So we start with a 6. We add 1 ton to them. Because the thing is that it's going to give us a lower total cost. So it's better to supply there. That's what it means. It's better to supply there. So we give it a +1. Once you give it a +1, you increase the total cost. The total supply. You increase that total supply. Once you increase the total supply, you got to find a way to bring that total supply down, to balance it. Because whatever you've done here, you see that the total supply has been increased. We've not spoken about demand. We are not talking about demand. Okay, we are talking about this one. So you can see that the 600 actually has changed, but we've not indicated that it's changed. Then, to avoid a constraint violation, we got to balance the supply constraint by supplying 1 ton along that same row. So now the supply has increased. We want to balance it. And to balance it, what you do is that you subtract 1 because you've added 1 to that row. You subtract 1 from that row so that this one will come back to 150. Which one are you going to subtract from? You have to choose the lowest. And the lowest will be what? 8. So when you add +1 to the cost of 6, but of course you're not actually adding it to that cost. You're adding it to the cell, and then it will increase the tons. The next one with the lowest cost will be the 8. So you have to subtract 1 from the 8. So when you look here, you subtract 1 from this 8, which has a ton of 25 already. The moment you do that, you reduce the 150 down from 151, you bring it down to 150. Okay, so now you've cut it down. But then what you've done is that you have also reduced the column here. Because by minusing this to balance the 150, you have reduced 100 to 99. Okay. When you reduce 100 to 99, it means that you need to find a way to bring that 99 back to 100. Wow, something is happening here. You're going to see very soon. So it will keep doing that. Of course, you should know by now which one we are going to touch. Okay, we come back here. We do +1 here. But when you do +1 here, again, you increase this 175. Are you guys with me?
Yes,
Because you are doing +1 here to be able to, you are doing +1 not to the empty cell. Please remember, you started with the one that would have been lowest. But at this case, you are looking for the lowest, even if they have already been used. And I made that point here, that you arrive at a solution when you can only add to and subtract from cells that already have allocations. Already have allocations. Now remember that the ones we started with, let me just go back here. Okay. If you look at the one we started here, there was no allocation to 6, but we started with 6 because 6 had the lowest cost. Okay. But after that lowest cost, subsequent ones, even if it has allocation, you're using those that have an allocation. All right, let me move on. So the question is that which one has got allocation? This one here. Okay. On this level here, the lowest cost is going to be the 5. And therefore, you subtract this one. That's the one you are touching. Sorry, you add +5 to the 75. And when you do that +5, this one goes back to 100. But once you do that, you move the total here to 276 instead of 275. Okay, so now you need to find a way to bring that one down. Where do you think you will touch to bring it down? Now you should have the obvious work. Where do you think you will touch to bring it down? Where do you think you will touch to bring the 276 down to 275?
You touch the 200, that's 4.
Exactly. Very good. Okay. So now you're getting the point. So the whole process, you see, the whole process is like crossing a pond. Suppose you have some stones and you have some pond, or you have some lagoon and there are some stones in the lagoon. You have to jump and jump and jump. It's like you are stepping on stones. That's why it's called stepping stone method. Okay. To only the allocated cells, you are stepping on stones. And so you move an angle from 1A, in this our case. We started from here. Okay. This 1 and A, cell 1A. Then you go to cell 1B, as you can see. Then from cell 1B, you went to cell 3B, and you can see it here. From 1B here, we went to 3B, which was a plus. And then from 3B, we went back to 3A, okay, which is here. The one Simon mentioned. And then you rotate that one back. So the cost associated with each one of them, you will check. So the cost here was +1 minus 1, +1 minus 1. Okay, so let's start with +1. That one is what? 6 minus 1, because it has a minus. This minus is multiplied by the 8. Okay, so you get -8 +1. +1 is multiplied by 5. So you get +5. Then -1. -1 is multiplied by 4. You get 4. When you add all of them together, you get -1, which is a value that you see here. So overall, the cost after your, because by the time you get back here, okay, by the time you get back here, this whole thing has balanced. Remember that this +1 took this one to 200, but it's brought it back now to -1. So the 200, sorry, it took it to 201. It brought it back to -1. So everything is balanced backward. But what you've done is that when you add the cost to it together, you've been able to reduce cost by -1. So you go and take your total cost, and then you realize that the total cost will be reduced by $1, which proves that at least, for this example, that the initial feasible solution was originally not optimal. It was feasible. It was just feasible. So you got to make sure that all the empty cells are assigned or evaluated. The one with the greatest cost reduction becomes the entering variable, or becomes the variable in question. So you can see the same conclusion that I have here. This is a final allocation. The idea is to find the cell that reduces the cost the most. And that is why when you find the cell, you got to make sure that you do not also undermine the balanced, transportation that we do. If such a cell exists, it will be picked as the entering variable. If it doesn't exist, 1A will be selected. For example, suppose that we didn't get anything, then we have that 1A selected. Therefore, the remaining empty cells must be tested like 1A. So at the end of the day, this is what you get. If you go through, you got to go through them. Okay, let me just show you something. You got to go through all of them, and you have plus here, minus here, plus there, minus there. Okay, and we go through this. I mean, we had to do multiple ones. You remember that the minus we touched on plus. Do you remember? If you can remember, that when we're going through the first iteration from the +1 for the first cell here, we went to this 8. Do you remember? I don't know if you do.
Yes.
But I went to the 8. And then you came back down here And then eventually we curved here. Now, if we go
Yeah.
through some of the other ones, instead of the 8, you rather go to here and start manipulating them to get back, you're rather going to see that some of them are going to give you more cost. Like one of them gave you what? Plus $4. Plus $4 means that, if you compare that to this one, okay, this one is -1. So cost rather comes down. But if you look at this one, cost has rather gone up. Okay. So you got to go through them, and eventually you will see the one that gave you the best cost. That is when the cost is reduced. And which one is that? Is the one that had a $6. So the $6 now be multiplied by the 25. Then we had what is it? Another one which was 8. 8 didn't give us anything. So this was the one. Basically, this was the one. Okay. It gave us 6, 25, 10, 25, 11, 75, 175, 4, 175, 500. Okay. And that gives us 4,525. And that one will be the one that will give you the cost. Of course, remember that it gives you optimal solution, but you will have multiple optimal solutions. Oh, no, not multiple. You will have multiple solutions. Well, the solutions are still optimal. And then you take the one that is the lowest. So that is what is known as the transportation model. The transportation model. Now, the transshipment model is an extension of the transportation model. Yes. Yes.
Please, can we go back on the model? Go back again, please. Go back again on the work that we did. Yes, this please. So from the analysis, I realized that is +1 -1 +1 -1. So can it be that you can increase it to be like +2 -2 +2 -2 and do the calculations and see whether that can bring you more minimal cost? And if so, you do so until you get to a saturating point. Or you just do one like this and it
You just
works
do
in
one.
interest.
You just do one. It's a total that will give you the cost. You just do one, but it is when you now add them all together, you multiply it by the corresponding cost, that will give you the cost, the net cost that you're looking for.
So in essence, I understand, docs, but in essence, it means that now when you are doing the transportation, you are sending only 1 ton to 6A. Looking at this
For this
model,
example,
right?
yeah. Yeah.
And what of if you rather you send 2 tons to this A and reduce that 6 that is 4A by 2 ton? That one will rather give you the most minimum cost. Should
Are you
you
sure
rather
that will
use that
give you
model?
most minimum cost?
That's what I'm saying. Maybe when you do that calculation,
Remember that whatever you have to multiply it by the existing cost. So if I multiply 1 by an existing cost, I get a lower number than if I multiply 2 by an existing cost. If I do 1 times 6, it gives me 6 than if I do 2 times 6. That gives me more cost.
but I think in that the negative here, so you realize that this -1, so it is -120. That I'm talking about the 25B. So if that place, assuming becomes
okay, let's try that. So let's try what you're saying. We take 2 multiplied by 6, right?
Yes, please.
And then we take -2 multiplied by 8. That's what you mean?
Yes, please.
Okay, let's try that in my work. 2 multiplied by 6, -2 multiplied by 8.
Then +2 multiplied by 75.
+2.
Then -2 multiplied by 4.
It's not 75, it's 5. I mean,
It's 5. Yes, please.
and that's 1 multiplied by 4. Hey, sorry, -2. multiply by 4. Right? So this gives you 12 minus 16 plus 10 minus 8. What do you get?
Minus 2.
Minus 2.
Yes, Doc.
Okay. Does that balance?
Yes, it will still balance.
Okay. But then if I take 100, if I take a 10, that 10 becomes better. But you shouldn't.
Yes, please.
No, but the example you are giving shouldn't use the same root. We are not talking about using the same root, because the reason why we are using the negative one is that whatever you are using now, you are using the same root. So obviously, when you increase the number, okay, whatever you are going to get is going to be, but it's the root we are looking at. The root you are using is still the same root. It's only that you've increased the number from 1 to 2. But the same root. But we are looking for a situation where you change rather the root and you still get a lower number. Do you get what I mean?
Okay,
Even if you
Doc, I
take
get
your
it.
2, even if you take your 2, this cannot necessarily be a lower number unless you use a different root, and that gives us a lower number. It's not the increment of the 1 to 2, but it is the root different from the original root you passed that eventually leads you to what you want. So instead of actually using this root, you can use from here. You don't go here. You rather come here. Okay, still using that same number that you used for the previous one. And if that yields you the answer you're looking for, then that's it. The lowest cost, then that's it. Do you get what I mean?
Yes, Doc.
Yeah. All right, okay. Let's work the last one. So for transshipment model, guys, there's nothing to calculate there. This is transshipment. Transshipment simply means that you have something in the middle that connect the supplier to the demander. Simple. You connect the supplier to the demander. You connect the supplier to the demander. Okay. So remember when I didn't even look at transshipment because that one is just the same as transportation, to be honest with you. It's the same as transportation method where you try to cut down. You try to bring an intermediary between the supplier and the demander. My interest is more of the next one, which is assignment problem. Assignment problem is more of assigning some groups of people to do certain things in such a way that whatever they are going to do will bring a lower cost or a lower distance. I'll give an example. Suppose you have a couple of pastors, maybe 10 pastors, and each one has got a home that they stay. And this is a pastor group. And these 10 pastors, that weekend, they all they work together. They are all assigned by the chief pastor. And they are all supposed to go and give a wedding talk. And the wedding talk are scattered also across the country. And each one has to travel a distance to get to that wedding talk. But then the chief pastor wants to assign each person to the wedding talk with which he is closest to. Is want to assign which way. So sometimes you give some job to some people because they are good in that job. But in this case, we are rather giving a job to some people because the lorry fare will be smaller. So if you are closer already to East Legon, then handle the East Legon one. But why will you go and handle the Kaswa one when there's somebody who is already living in Kaswa and you move from East Legon to go and do Kaswa? That is the principle behind the assignment problem. So the assignment problem is basically a balanced transportation problem. And that's a good thing about us. The balance here means that every supply constraint will be equal to 1. And every demand constraint will also be equal to 1. Take note. So if you have 1, 2, 3, and 4, when you set up this equation, you set it up equal to 1. When you set up this one, it'll be equal to 1. When you set up this, it'll be equal to 1 because each person is assigned 1, 1, 1. And so the constraint, the good thing about assignment problem is that the constraint is equal to 1. All the constraints are equal to 1. And look at this point here. It involves determining the most efficient assignment, the one I said, of people to projects, assigning salespersons to territories, auditors to companies, contracts to bidders, jobs to machines, heavy equipment to construction jobs, one team of official to each soccer game. Okay, so every week the Premier League is played, but you want to assign referees, but the referees must be assigned in such a way that the referee going to handle this game is not going to travel too much. You know, but you also have to make sure that the referee is not from that area. So, especially the Champions League, if the game is being played in Spain, you make sure that the referee is not from Spain. But then you also have to make sure that the referee coming is also not coming from far away, but is also coming from another country. It's a very, very hefty work, but that is how it is. It is an M by M assignment problem. Okay, and the way to solve it is using something known as the Kunz-Hungarian method. The Hungarian method can beautifully be used for assignment. Okay, let's get an example. And there's a theorem that you got to note here. If a number is added to or subtracted from all of the entries of any one row or column of a cost matrix, then an optimal assignment has been reached. Okay, and the resultant cost matrix is also an optimal assignment for the original cost matrix. We'll see this one as we go further. The guy, Harold Kuhn, he published his work in 1955, known as the Hungarian method for the assignment problem, published it in the Naval Research Logistics Quarterly. He described the algorithm, the step-by-step procedural analysis for constructing a maximum weight perfect matching in a bipartite graph. He did that. And so today we use the Hungarian method, to solve such assignment, which is a purely minimization problem. Either you minimize costs or you minimize distance or something else. Okay, let's take a typical example. This is a game they play, a basketball game they play in the United States. They normally play it in the evening. In the conference office, they are in charge of all the games. And they normally assign 4 teams of officials to the 4 games in a way to minimize the total distance traveled by the officials. So take note that we have 4 teams of officials. Okay? Just like you might think about a football game, these days we have the referee, we have the linesmen, and then we have those at the poles. So that's like 5 teams of officials. But for this particular game, we are talking about 4 teams of officials. Okay, so there are multiple teams. The distances in miles for each of the team of officials to each of the game location is shown here. So officials in Group A, they will have to go to one of these possible game sites: Raleigh, Atlanta, Durham, or Clemson. Now, looking at the table from hindsight and knowledge, where should officials, Team A officials go? Where do you think they should go? To cut down.
Atlanta.
Atlanta. Very good. What about Team B?
Since Atlanta has been taken.
What about Team C?
Team C, same Atlanta.
I won't ask you for Team B. So you can see that since everybody has to go to Atlanta, who should go to Atlanta? I know what you are going to think, but let me see from you. Since everybody has to go to Atlanta, who do you think should be properly assigned to Atlanta?
Dog official B.
Team D.
D for dog.
Okay,
Yes.
D. Yes.
You would have made the biggest mistake of your life because you just looked through the vertical one and just selected the lowest there, forgetting that the others are going to go to other places. When relative to the original distances they have, they may be punished. Does that make sense?
Yeah.
Yeah. If you take 65 for D, and you are saying that the next one, you are going to select 70. And then you're going to select a lot small. No, because matching it against the other numbers, you got to know which one must go where. And that is assignment problem. So how do you do the assignment? Well, first, we are going to define the decision variables for this transportation problem. It's actually assignment problem. Because note, we said that assignment problem is a transportation problem where every constraint equals to 1. Okay. So we are going to define the decision variable and develop the graph. Now, looking at this, how many constraints are we going to have? How many constraints are we going to have? How many circles? 1, 2, 3, 4. That is officials. Sites. 1,
We have 2.
3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So how many constraints are we going to have?
Eight constraints since the nodes.
Yeah, if you don't take care, what you wouldn't know is that officials A have got a chance of going to all 4. That's what I mean by official A has gotten the chance of going to all 4. So A can go here, A can go there, okay, A can go there, and then A can go there. So how many decision variables are we going to have? How many decision variables?
16.
16.
16. Okay. So now let's look at the answers to this because we've already identified the easy bit. I mean, defining the decision variables. Yes, I have it.
So, please, is there any difference between like the game and the sites?
No, it's the same thing. It's game
It's the
site.
same thing.
It's game site.
Okay. Okay.
I just couldn't break it down, but it's game site.
Okay. Thank you.
All right. So you can say that let Xij be the team of officials I to game site J. Or you can simply say that let Xij be officials, assigned from node I to node J. You can make it simple like that. Okay. All right. And then you draw it. So this is a drawing. Now here, I decided to rather bring the distances closer to the first element. Okay. But use the numbers. Use the numbers, like I said before. And then you have the decision variables at the end, but it's going to be the same thing. If we are to use the numbers, it's going to be x15, isn't it? x16, x17, x18, like that. And then you assign all of that. So you said that you have to write the decision variables. You are going to have 16 decision variables. And that's true. Okay, you can count from here. It's 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So 16 decision variables. That's what you're going to have. So if you have to write the objective function, it would be all 16 decision variables, as you can see here. So we are minimizing the distance for all these 16 decision variables. Okay. Who is not clear? The next one now is to subject to the constraint. Now, again, the same principle. How do you do the constraint? You take this one, you look out for the items leaving this arc, or you take Raleigh, you look out for the things coming into it. So Raleigh will be what? X15 coming into it, plus X25 coming into it, plus X35 coming into it, plus X45 coming into it, equal to what? Equal to what?
Sorry, I was muted. 1.
I was 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1 Okay, equal to 1. That's how it is. Okay, so you set it up all equal to 1, and that's it. You're going to get something like this with your non-negativity constraint. So assignment problem is very easy if you understand the principles. Okay, so but that doesn't solve it. Okay, so you're going to do something we call row reduction, and then so the approach. Remember, we said that you use the Hungarian method to find it. So you're going to perform row reduction by subtracting the minimum value in each row from all the rows. So let's get that first. Row reduction, you subtract the minimum value in each row from all rows. Let's do that first. Okay. Before we come to if there's a minimum and all of that. So let's take this one, row reduction. You're going to perform the minimum value of each row from all rows. What's the minimum value here? For the first row? 90.
90.
Okay, so you subtract 90 from all of them. 90 itself will have what left?
0.
0.
So that's the first one here. You do that for all the rows as well. So I did it for the first row, the second row, the third row, the fourth row, the fifth, and all of that. Is that one clear?
Yes.
Okay. Now we go to the next one. Perform column reduction by subtracting the minimum value in each column from all columns. So let's continue from here. The minimum value in each column here, Raleigh, is what?
30.
So 30
sorry,
will have
15.
what?
Dog, 15.
So 15 will have what?
0.
0.
So what to be here? What to be here, here, here? Here will be 0. But what
So
to be?
105.
Yeah.
15, and then 55.
That's it. Now, here will be what? 0, 0, 0, 0, 0.
Yes.
So, see, at the end of the day, we are claiming to have zeros. That's the whole idea. Let's go to Durham. You know what you get there? It's the same principle, isn't it? You go to Clemson, the same principle. So, Durham, you take which one? Which one will be the minimum?
So 35.
What value will be here? At the
5.
5. Okay. So, you get 5, 0, and then here we what?
25.
25.
Then
and 65.
65. And then the rest, you can continue as it is. Now, if you do that nicely.
It's 55, not 65.
Yeah, 55.
Okay. So if you do that nicely, you're going to get something like this. So far, so good. Now, let's go to the next step. The next step is cross out all the zeros using the minimum number of horizontal or vertical lines. This is critical. This is the tough part. Cross out all zeros using the minimum number of horizontal or vertical lines. The minimum number of horizontal or vertical lines. So now when you go here, this is where we have gotten to. Where is that? No, here. So cross out all zeros using the minimum number of horizontal or vertical lines. So when you take this one, which has got zeros, anywhere there is 0, you're crossing them. So here has got zeros, right? So you can cross it. That's gone. Where else has got zeros? Which rows?
The bottom line.
D has got zeros. Which one else?
C.
Row what?
C has
Row C also has zeros. So now you've crossed all of that. That's the point. Drop that. So now you can see that we have gotten this. Okay. Let's go to the next step. It's using the iterative method of Hungarian, or precisely the simplest principle, the same thing we used to have in the principle. Now, if fewer than m lines are required, okay, now m here is a number of rows and columns. The number of rows and columns. If fewer than m lines are needed, subtract the minimum uncrossed value. Now, the minimum uncrossed value are those that were not zeros from all other uncrossed values and add this same minimum value to all the cells where two lines meet. This is a final step, but it's tough. And leave all other values and repeat the steps again. Watch the word. If fewer than m lines are needed. Now, m lines here is, remember, your rows and columns. Okay, m is the number of rows and columns. Now, right now, the way we've canceled it, we have 2 rows and 3 columns. Do you remember? We have 2 by 3. Oh, you've forgotten. I need to go back there again. We have 2 by 3. Let's just go back. Oh, where are we? Yeah. So you see, now we have 2 rows, 105, the row A and B, and the columns Raleigh, Durham, and Clemson. So now let's go. We have 3 lines, if you check it carefully. Okay. You see, we have 3 lines. 1, 2, 3. Okay. So, which is not a unique assignment. Why? Because there are 4 rows or 4 columns. So we need to have 4 lines. That is a minimum we should have. That's the point that was being made. So we have to subtract the minimum uncrossed value. Now, when you check the values here, which one is the minimum uncrossed value here? Those that we haven't crossed is 15. Okay, so you take this 15 and then you will now, he says that bigger than the 15 and plus. Okay, but the key point is that you take the 15, you will add it to values where the 2 lines are crossing. And where are the 2 lines crossing? These 2. These 2 here. You're going to add the 15 there. So when you do that, you get back what? 15 here. Are you guys with me? And I'm all that.
Okay,
No, it's very complicated.
Yes, it's supposed to be complicated. It's called Hungarian method. Now, where do you even start from? You are hungry. Okay, let me go back here. You are going to take that 15, you subtract the 15 from everybody. Now, why did we take the 15? The reason why we took the 15 is that the number of crossings that we did were not up to 4. They are 4 by 4, but we didn't get 4 lines. And so the rule says that take the line that was not crossed, any line that was not crossed, the lowest number there. The lowest number there. And then you take that lowest number and you will subtract it from those that are positive values and add it to those that are zeros. So you have 15 here, and then you have 15 here. Those are the lowest. So you take that 15 here, you subtract it from 15. Now you add it to the 0 here, you add it to the 0 here, you subtract it from 75. You get 60. You subtract the 15 from 55. You get 30. You subtract the 15 from 25. You get 10. You subtract the 15 from 105. You get 90. You subtract the 15 from, what do you call it? From 15, you get 0. And then you keep going. Now here, watch it here. Wherever you have crossed, wherever this thing has been crossed, you add it there. But wherever you have not crossed, you will subtract it there. Now, why are you taking that? You are taking that because you want to clear these numbers towards the 0 point. Okay, so this is what you get. So you can see that here, whatever we have here, okay, you subtract it here, you add it there. Okay, you subtract it here too. Here, 35 you add because it has been crossed already. Okay, here you add, here you add, here you add. So this 25, this 5 becomes 20. Okay. Is it 5? Sorry. Hold on. It's 15 here. So here you add, sorry. You add. You add, right?
Yes, you add.
You add. Here, you
You
add
add.
by weight. Yeah. I don't know why this thing, oh, I didn't type it well. Let me see that. So 25. Okay. You take the 15 here. It's from that number. Okay, so watch this. You take the 15, you subtract it from 15, you add it to, you subtract the 15 from here, you subtract the 15 from there, okay, but you don't touch where it is positive unless it is 0. Hold on. I may have made some typos myself. Hold on. But the key point is this. Let me just go back here so that we don't. It said we subtract the minimum uncrossed value, which is 15 in our case, from all other uncrossed values, okay, that are bigger than the 15. So if you are bigger than the 15, we will subtract it from you. If you are not bigger than the 15, we'll leave you. So when you come here, for those that are uncrossed, so here we'll add it. We'll add it. Here, you are bigger, okay, than the 15. So because you are bigger than the 15, we will now take that number and then we'll add it. Okay, all those that are 15, we add. These ones, like 5 and 10, they are not bigger than the 15. Okay, so 5 is not bigger than the 15. So you don't subtract, you don't add. I mean, ideally you would have added, but you don't add. Okay, it's a number. 10 is also smaller than 15, so you don't add. But everything here that is 15 or more, okay, you will add to them. And then those that are zeros, okay, you subtract from that. So if you take the zeros become, sorry, did I say add? Those that are positive here, you will subtract. But those that are zeros, you will add. But then you will subtract provided it is 15 or more. That's when you subtract. That is why we didn't want to do this, because otherwise you're going to get negatives. Okay, and non-negativity is not allowed. So here, 25, you will add 55. 25, you subtract 55, you subtract 15, you subtract 75, you subtract 105, you subtract 15, you subtract. Okay. Now, uncrossed, those were uncrossed. Crossed, you will add provided that it is bigger than 15. Here, you will not add because it's not bigger than 15. Here, you will not add because it's not bigger than 15. And that is what you have here. Okay, it's a little bit tricky, it's a little bit abstract, but that is how it is. Okay, once you've done that, the next one is now 4 lines. So let's see 4 lines, because you want 4 lines that have got zeros. So you can see from here, it says that because there are 4 rows of 4 columns, so we need 4 lines minimum. And when you check here, we have 4 lines or 4 unique assignments. And look at it here. Because at each section, you now have zeros. That's the whole point. If you compare that to this, we don't have zeros everywhere. But here at each column, check each column, there's a 0 somewhere. Okay. And check each row, there's also a 0 somewhere. That's all you need to end the iteration. So here, 4 lines or unique assignments can be made. Okay. And look at it. If you look here, Team A. Okay. Team A, you have 90 and you have 40. Now, the temptation will be that you assign Team A to what? 40. But if you assign Team A to 40, you're making a big mistake. Why? Because there are other smaller values here for Durham. Because once you assign Team A to Durham, no other team can go to Durham. Okay. So once you see smaller values there, you don't assign. So team A will have to go to where? 90 here, Raleigh. Team B will go where? Between 10 and 60. Even though there's 5 here, it will go where? And I'm more that.
80.
I will hold on. That's what I would have done. I'll hold on. Then team C. Team C, where would it go? The lowest would be what? That one is obvious.
Log
Clemson.
10.
Good.
Yeah.
Then now it's between team B and that. Each of them would have to go to Durham.
Log D.
D goes to
That's
Durham.
5. Yes.
And B goes to
Dog, why
where?
is it that you are not using the zeros rather, since they are the lowest?
You are not what? Oh no, the
Using the
zeros were
zeros.
designed for you to, you created the zeros. You created the zeros so that you will see the numbers that have been assigned, the distances that have been assigned. So we are not looking for zeros. We are using the zeros to clear what we want. It's like a method of elimination. The zeros are helping you to eliminate the distances that are not needed. Then you now get the distances that are needed.
So in essence, where there is zero, so for example, on row A, it will not be advisable to assign officials to Atlanta and Clemson. Is that what is it means?
Wait, I get your point. I got your point. Let me see. Yes. It's important to assign officials A rather to Atlanta because it has a 0 value there. But then Clemson also has a 0 value there. So question is, why don't you assign Atlanta to Clemson? It makes sense to assign officials in D to Clemson, officials in C to Durham, and officials in B to Raleigh. Let's match that. You're right. I mean, I missed that. Okay. It makes sense to assign officials in.
Log B should rather be Atlanta so that the D can be Raleigh.
No.
Because if B goes to Raleigh.
A should go to Atlanta.
Not Clemson.
Why should he go to Clemson? Because
okay. That's because the mark for Doc. D also has a 0 under Clemson, so that one can go there.
Did we have costs? Did we have costs? No, we didn't have costs. Yeah. You said D can what? Sorry.
D can also go to Clemson. It has 0 under Clemson.
Yes, D will have to go to Clemson. It has 0 under Clemson. Okay. But I need to give you a reason why D has to go to Atlanta than it has to go to Clemson. Because of the distances associated between, okay, so for example, if D goes to Atlanta, if A goes to Clemson, as you are saying, that means Clemson is taken, isn't it?
Yes.
So you'll be forced to take D to where?
To Raleigh.
Hello.
And then B to where?
And then B can go to either Atlanta.
You can't go to Atlanta.
Yeah, B can.
Because you've assigned it.
No, Doc, I haven't assigned Atlanta. I assigned Clemson and Raleigh. So it's left with Atlanta and then Durham.
That's Clemson and Durham.
Okay.
Okay, so where would what go?
Okay, so for me, I would have made A, Clemson, B will go to the Atlanta, C can go to the Durham, and then the D can go to the Raleigh. So it will be 1-1.
Okay.
and they'll all be zeros.
Let's take the one with the highest, what do you call it? The one with the highest distances so far. Let's take the one with the highest distances, and then you get a point.
We have.
So you have all of these game sites. You are going to assign to those that have got a zero distance.
Yes.
But to do
So
that,
is it that there is a rule that, okay, for each rule, look at the one with the highest distance.
Look at the one with the cumulative higher distance.
Yeah, cumulative higher distance, and let them choose first.
Yes.
Is that a rule?
Yes.
Okay.
No. When you say, is that a rule? To be honest, when you say, is that a rule? I've not seen that documented as a rule, but that is the rule that my knowledge tells me that it has to be. Another, if I tell you clearly that it is a rule, you will accept it, which it is. But I just don't have the references for that.
Okay.
Yeah. But I can also write the book. So that's what I mean by, it is, but I don't have the references.
Definitely.
Yeah. But it is. That is it. That is a most sensible way to go. You add the one with the highest, and then that one makes that move. But it chooses the one that is a zero. Okay. And it has the choice of this Clemson and that. But that must tally with the original distances that you had. And in the original distance, and you realize that all of them wanted to go to Atlanta. That alone gives the impression that he would have taken that first stop. So you take Atlanta. Once Atlanta is taken, it can no longer be taken by anybody else. The next person with the next higher distance make a move. That is C. C has to make a move by choosing Durham, because that is the only one with zero. Then it's left between B and D. The one with the higher distance is B. B has to make a move. He has Atlanta and Raleigh. The only choice is Raleigh. And now D has to come in. All of them has been taken. D takes the point of Clemson. And it has the lowest cumulative distance. That is the way. Once you've gotten these choices, okay, you now go back to the original and go and check the distances allocated. Remember that A chose Atlanta. So once you go back here, the original, A chose Atlanta. So you take 90. B chose Durham, right? B chose Durham. No, B chose 100. So it is 90 here. Okay. It is 100 there. C chose 140 there. And D chose this 120. So in your objective function, you're going to substitute these numbers to find what? To find the minimum distance. And please remember that the minimum distance, all of them, the x's were 1. Okay, the x's were 1. And so it chooses that one in that regard. Just a second. So when you do that, you summarize all of them, and then you're going to get the final one. You draw those that have been given. Okay, now you can allocate each one. Okay, you can allocate each one. Just hold on a second. All right, so you add them, you can do the drawing, and finally, you can have your extensions and everything that you need to do. You can check an example. This is an example question. Okay, you're a sales manager for the toy manufacturer, Crack, Cape Coast, Boko, and all of that. You have all of these things there. Okay, and you can represent this in a matrix, and then you have a question, and you have to do the assignment and all of that. This is another Hungarian approach that you can check later on. This is another Hungarian approach. Just look at it. Okay, I've added a question in there for you to look at it. That's it for today.